Well, that's usually a problem in software. So now, what happens when we, instead of Alice and Bob sending back and forth bits, what happens when we allow to send qubits back and forth? Can qubits reduce the communication for certain Fs? And actually, at first thought, you might think, no, this cannot help, because if I prove that classically I need k bits to solve this particular Boolean function f, then quantum mechanically I will also need k qubits, because I cannot compress these k bits into k minus 1 qubits by whole level. However, this is false, and I want to show you this first example that we actually, it's not the first, but it's the first larger one, where actually this is not true, this reasoning, and we have a function which I call equality prime, which is 1 if and only if still x equals to y, but it has the promise that the Hamming distance between x and y is either n over 2 or 0, and if it's 0, of course, then they're equal. And what you can show is that this particular problem still needs n bits classically to solve, but it can be done with just logarithmically many qubits. And then this sort of leads to better and better examples, but I think it's interesting to show this one. First, let me show you how the quantum protocol works, and then let me tell you why a classical protocol requires many bits. So the reduction is of course to the Deutsch-Jozsa algorithm, which I've shown to you. And observe the following thing. If you have, here's Alice's input, and here's Bob's input. And now if you were to bitwise XOR their inputs together, resulting in the string Z1 up to Zn, then notice that if the Hamming distance between x and y is n over 2, then Z is a balanced string. And if the Hamming distance between x and y is 0, then of course Z is a constant string. Okay? So if we, meaning Alice, would have access to this string Z, if she were just able to make one query to Z, then she can run Deutsch-Jozsa algorithm and figure out whether she's in this case or this case, and hence determine whether the strings are equal or not. Of course, she doesn't have Z, but she has X and Bob has Y. So how does this work? So here's the quantum protocol, and look at the similarity with the algorithm. So first Alice prepares a state minus 1 to the xi I. And this state she can prepare by herself, because she knows the values xi. So she can actually construct a state that looks like this. And now this state she sends over to Bob. And then Bob, he doesn't know what xi is, but he knows what yi is. And he can actually transform this state, and he can add to the basis state I, he can add a phase of minus 1 to the yi. Again, this is something that Bob can do to the state he has in his hands. He doesn't know xi, but he can add to the basis state I, he can add minus 1 to the yi. And now look that the state that he then has in his hands is minus 1 to the xi plus yi, is really this state minus 1 to the zi. Okay? And also remember that this was exactly the state that you get back after the first query in the Deutsch-Jozsa algorithm. You get a superposition over all states, and in front of state I you have minus 1 to the zi, if you wanted to know whether zi was balanced or constant. So, well, in principle Bob can now finish the Deutsch-Jozsa algorithm, or he could also send the state to Alice, and then she finishes. But then she finishes the Deutsch-Jozsa algorithm when she measures a 0 on all zeros, then she knows the string was constant, and if she doesn't, then the string was balanced. So she has all information she wants to know whether these two strings are equal or not. Okay?
But what we are sending?
So what we are sending is sort of Alice.
Some physical picture. What is here sending?
So Alice prepares this state.
Yeah.
sends it to Bob. Then Bob changes the state.
Yeah, but the state of
into
which
this state.
system?
So here is a state that runs over all n-bit.
So it looks like a state of n qubits.
No. We need
This is
log n qubits.
This is a state of little n qubits.
Yeah, we should prefer it.
Which is right.
Yeah.
And I had my capital N, but by the same definition of.
So when he writes
Ah.
I in this cat I,
Yeah, we have
I is a binary,
independent, yeah.
binary string, so to say.
Yeah. So this is a state that consists out of little n qubits.
Yeah.
So
And we compare it
and
to
qubits.
the n bit strings, yeah.
Yeah. Yes. And the string and the strings x1 up to x capital N is 2 to the n bits. Okay.
Yeah, but I still try to understand how what is physical. Is something like that several photons are sent from Bob to Alice, like in your crystal picture, something like that. The polarization means 1 qubit.
You should prepare an entangled state of these photons.
Yeah.
But so we should send them somehow at the same time or what?
No,
We
you can
don't-
transmit them
you can transmit them
in
one-
order,
one by
but
one.
you should conserve the entanglement.
Yeah.
If your transmission protocol destroy an
You
entanglement,
are saying now about something
the
physical or about some just theory. So is it possible to send photons sequentially, keeping them entangled or what?
Yes. The answer is yes, you can. Only not that many. Maybe 2 or 3 for the time being.
But at which interval we can we send today one and tomorrow the next?
Well, I think that the physicists usually talk about nanoseconds. So, but that's just the scaling factor, right?
Yeah.
They cannot preserve entanglement for so long. But for a little while, maybe 10 times longer than that. But then in theory you could postpone it, and they're working towards making these times longer and longer. So physically, what is happening? Alice prepares the state, sends it to Bob, and then actually Bob can already compute the answer. So that is here. So Alice sends n bits, little n bits, which is log of capital N qubits, and actually that's the cost. In the protocol, I did it more stupidly. Okay.
But then the question is, somehow you clearly send 2 to the n bits information in the state of n qubits. So what then is the meaning, exact meaning of the theorem?
Well, the point is I don't send 2 to the n bits of information because Holevo tells us that in little n.
Yeah, but what is the
Qubits.
exact statement? Something is impossible according to Holevo theorem. But what is impossible? What is the exact meaning of this theorem? What does it say formally? Because
well, formally it says that if you have a message that contains n bits,
yeah,
then what he does is he says what is the uncertainty that you have about this message when I only send say n over 2 qubits, then the uncertainty is very high. So you can talk about